Problem 2. You will notice that the matrix in this problem is actually a flipped version of the matrix in problem 1. I took the rows of the matrix in problem 1 and turned it into columns in the matrix in problem 2. And of course, I had to come up with an entirely new right-hand side. So once again, let's take a broad look at the system and see what we can expect from the solution, and only then do Gaussian elimination. So here we have vectors in R5, and we have only 2 of them. They are linearly independent because not one of them is a multiple of the other. So we have 2 linearly independent vectors in R5. So if we have a solution, it will be unique because the null space is the trivial null space consisting of the 0 vector alone. But we'll need a little bit of luck to even have a solution, because since we only have 2 vectors in a 5-dimensional space, they only span a 2-dimensional subspace of the entire space. And this system will only have a solution if the right-hand side, by luck or by special design, happens to be in that column space. So simply by looking at these columns and the column on the right-hand side, it's not easy to see or guess whether the right-hand side is indeed in the column space. Well, that's what Gaussian elimination is for. Gaussian elimination will reveal to us whether the right-hand side is in the column space of these 2 vectors. That's the whole point of Gaussian elimination, to figure out all the relationships among the data that are not evident to begin with. So let's begin our Gaussian elimination, and I think we'll be able to squeeze 2 of these systems on one line. Once again, I'll just make a copy. Okay, good fit. All right, so the first step is, of course, to identify the pivot. It is this 1, so let's make it bold. And this 1 will be used to eliminate all of the numbers below it. So the first step is to subtract 2 of row 1 from row 2, which will eliminate this 2 and turn the 7 into a 1. The next step is to subtract 3 of row 1 from row 3, eliminating the 3 and turning the 10 into a 10 minus 9, which is 1. The next step is to eliminate this 4, which is accomplished by subtracting 4 of row 1 from row 4, which will turn this 13 into 13 minus 12, which is 1. And finally, to eliminate this 5, we have to subtract 5 of row 1 from row 5, eliminating this 5, and turning this 16 into a 1. And all along, we should have been doing all of the same steps on the right-hand side. And quite honestly, I forgot, but I got a little bit lucky because the entry in row 1 is 0. All of those row operations on the right-hand side would have had no effect. So a little bit of luck helped me in this case. All right, now let's move on to the second pivot, which is this 1. Let's make it bold. And let's now eliminate all of the entries below it, which of course is accomplished by subtracting row 2 from row 3, just 1 of row 2 from row 3. And the same thing here also results in 0. And to subtract row 2 from row 4, we'll get rid of this 1. And we're also so far getting lucky on the right-hand side, getting another 0. And finally, to eliminate this 1, subtract exactly 1 of row 1, 1 of row 2 from row 5, eliminating this 1. And on the right-hand side, the same operation will eliminate the negative 1. So we're done with Gaussian elimination because all of the numbers below the pivots are eliminated. So now we're left with just one step of Jordan back substitution, and that is to eliminate this 3 with this pivot, and that is accomplished by subtracting 3 of row 2 from row 1, gets rid of this 3, and now we have to do the same thing on the right hand side, subtracting 3 of row 2 from row 1, puts a 3 in this spot. So our solution and it's unique in this case, is xy equals 3, -1. Let's make sure that it's correct. Subtracting column 2 from 3 of column 1 results in 0, 6 minus 7 minus 1, 9 minus 10 minus 1, 12 minus 3 equals -1, and finally 15 minus 16 equals -1. The solution is unique because the null space is the trivial null space, and we're now done with problem 2.